Welcome to our panel. Very excited to hear the information myself today. Operation and maintenance of the future for the wind turbines. My name is Sherry Hunter. I am with the Bureau of Safety Environmental Enforcement. Lead a interdisciplinary team that is developing the policies and procedures, et cetera, for the compliance assurance program for offshore wind on the federal outer continental shelf. So we work hand in hand with the Bureau of Ocean Energy Management. BOEM will lead the environmental studies, the leasing processes, siting, and then Bessie oversees the work, starting with construction through decommissioning. That's the way we manage offshore oil and gas. This is how we'll manage the offshore wind industry. As everyone is probably aware in the room, O&M costs are about 30% of the LCOE of a project. This is according to an NREL study. We need to bring those costs down. So operation and maintenance is a key factor here, but also from the standpoint of the safety regulator, the less time there are humans out on the turbines, the less risk. So we are very interested in this topic as well. The operating and maintenance costs are very dependent on the effort needed for humans to access the turbines. As the turbines become more remote, the technologies that enable remote assessments are also improving. So we're very much looking forward. We have one less speaker. Unfortunately, he could not join us today, but we have 5 excellent presentations coming up. And I am going to apologize in advance if I mispronounce names. Please feel free to correct my pronunciation as I quickly go through everyone's bios. So Dr. Guiju Song, and I just got her bio this morning, so I'm going to read from my notes here. Currently the platform leader for offshore wind at GE Research, Dr. Song leads the strategic growth and multi-generational technology planning processes for offshore wind at GE Research. She supports transitioning the technologies developed by GE Research to new products for GE's offshore business. Prior to her current role, Dr. Song led a team to develop artificial intelligence and digital technologies to solve challenging industrial problems in the renewable energy and aerospace industries. She holds a PhD in optical engineering from the Chinese Academies of Science. Then we have Noah Myrent, technical leader in the wind energy R&D group at the Electric Power Research Institute, EPRI. His research focuses on the development of novel wind turbine digitalization and data analysis techniques that lead to actions for improved reliability, production, and cost effectiveness for the wind energy. Prior to joining EPRI, Noah headed the Onyx Insights Global Condition and Monitoring Program. And prior to this, he was a research scientist and wind energy research lead for the Vanderbilt Library for Structural Integrity and Reliability. He holds a master's in mechanical engineering from Purdue, and his bachelor's degree in acoustical engineering from Purdue as well. This Dr. Myrent, Annapolis. An associate professor at University of Massachusetts Lowell in the Department of Mechanical Engineering. He has led several research projects related to wind energy, aerospace, and automotive technologies at UML. He has been awarded the prestigious NASA Faculty Fellowship in 2022, and prior to his appointment at UML, he was with General Electric's R&D Center in New York, leading and supporting research and development projects with a focus on energy efficiency, dynamics, diagnostics, and power density improvement of machinery. Prior to this, he held positions at The Ohio State University and currently holds 3 patents, and several of these folks hold a lot of patents. It's a very impressive panel. And then John Garrity is co-founder and CEO of TagUp, Inc., which is applying new machine learning methods to improve industrial equipment of safety, reliability, and efficiency. Applications range across wind energy, power distribution, and water purification, among many others. Previously, John worked as a software product manager at GE Energy. He has an SB in physics and economics from MIT and an MBA from Harvard Business School. And last but certainly not least, Dr. Eric Hines, Director, Offshore Wind Graduate Program, Tufts University. Dr. Hines directs the Offshore Wind Energy Graduate Program, where he is a professor of the practice and now you're going to have to, Kintaro Tsunumi faculty fellow in civil and environmental engineering. Dr. Hines has over 25 years of experience in engineering innovative infrastructure, and he works at the technology/policy interface to develop systems-level design concepts and has received numerous awards for his work in industry-driven research. He received his undergraduate from Princeton University and was a Fulbright Fellow in Germany. He holds an MS in Applied Mechanics and a PhD in Structural Engineering from the University of California at San Diego. And just a couple of housekeeping items. There are no live questions, but you can submit questions through the Slido app, which hopefully everyone is familiar with at this point. So we'll start off. Dr. Song?
So good morning, everyone. As Sherry just mentioned, according to NREL reports, the OM cost contributed to 30–35% of the LCOE for offshore wind. So since you are in this room, so I assume you are very interested, you care about how to reduce the OM cost for offshore wind. On behalf of my research team, I will present our project called Enabling Condition-Based Maintenance for Offshore Wind. So I will start it off with the project background and our approach, the project schedule, and then following up with the project scope and our accomplishments. Lastly, I will share our project summary and the future perspective, because we just completed this project back to October of this year. So firstly, I want to thank DOE and NOWRDC Lyserda for funding this project, and also thank my program manager, Mel, and the previous program manager, Jürgen, for helping guiding this project to the success. So how we address the 35% of the LCOE contribution from OM? You may wonder, so condition-based maintenance has been applied for the traditional conventional energy generation industry and aviation. Why not do it in the offshore wind? Our objective for this project is to develop and exercise condition-based maintenance method and strategy for offshore wind. We cannot boil the ocean, but we want to focus and select one use case as a proof of concept. So since the blade leading edge erosion contributed to 5% of annual energy loss, we want to focus on blade leading edge erosion for proof of concept. But our underlying philosophy is not just to address one single user case. We want to build a framework technology that can enable condition-based maintenance for all the components, all the failure modes for the entire wind turbine. So our goal is to develop a sensorless, software-based solution. You don't need to add additional sensor on your turbine in order to do this condition monitoring and the maintenance strategy. So as I mentioned, the CBM has been applied to other industry. What's the challenge? What's prohibited us from using this to the offshore wind? The challenges are paramount. I'm just listing two core challenges over here on the right side of my slides. The first one is the data sparsity. Yesterday we heard in the US, there are 42 megawatts of install base. All the fleets are young. So based upon that reality, you don't have a long history of the turbine operation. That means you don't have lots of data for you to build a model, apply machine learning technology to enable CBM. The second challenge is about the model validation. As a scientific research, you can create the best, beautiful AI architecture. You can develop all kinds of machine learning model, use some of the data from simulation, from the lab to prove your model performance. But in the end of the day, if you want to convince the turbine operator, the farm owner to implement your model, you need to have the real field, real world data to validate your model so we can build the confidence to deploy the model. So my project will address these two core challenges. Before I jump to the project scope and also our accomplishments, I want to give you like a 1-minute elevator speech in terms of our approach. So our approach includes two phases. The first phase is about data generation. As I mentioned, data sparsity is the #1 challenge we need to address. In our project, we leverage the high fidelity physics model and then design a different combination of the wind condition, environmental conditions, and the blade roughness level. So blade roughness is a representation of the blade leading edge erosion. We run this model based upon all the different combinations and then output the turbine operation variables. Those variables include sensor measurement that's available right now on our turbine. Keep in mind, I just mentioned that we don't need to add any additional sensors. We want to use the existing data. These operational variables also include some controller estimation, for example, the pitch angle or generator torque, and so on and so forth. So this completes the first phase about generating data. The second phase is about the model building. In the model building phase, let's define the problem statement in a reverse way. So in this stage, we have all the inputs, all the variables acquired, available from the turbine operation. Again, those include the sensor measurement, control estimation. From the machine learning language perspective, we also include some derived features based upon the first two. So of course, each turbine is individual. We want to consider the specific wind condition, the specific environmental condition. So all this will be the inputs for my machine learning model. The model building stage is really about building a transfer function, ingesting all the model inputs to this transfer function, and the output will be the health condition of the blade. So once we have this model, now we can deploy this model in the field. We just run this model in real time. But for leading edge erosion, you don't need to run it in real time because it's a very slow progression process. You may run it every month. Then the output will be the estimated roughness of your blade. Based upon that insights, you can consider other economic calculation to optimize your maintenance strategy. So basically, that's the second phase. So our project started in April of last year. As I mentioned a moment ago, the phase 1 is really about the data generation. The outcome from the data generation is about let's observe what's available in the real wind turbine. And these observable variables show some behavioral changes based upon the blade leading edge erosion. So we completed the first phase last October and passed the go, no-go review. Then we went to the second phase this year. The second phase including building the model, calibrating the model, and also build a remaining useful life model for the offshore wind turbine. So in next 3 slides, I will update our results and accomplishments. So task number 1 is about the data generation with the high fidelity model. I mentioned a moment ago, we really consider the wind condition in real environment and also environmental conditions such as air density. So we use roughness level on this physics model to represent blade leading edge erosion. In our work, we designed 17 different roughness levels that represent the different severity of the leading edge erosion. With this simulation, we generate about 11,000 simulation data sets. So these 11,000 simulation data sets include 53 operation variables. All these variables are available from a real offshore wind turbine. So that completed our first phase. In the second phase, as I mentioned, for scientific research, you can try or create all kinds of AI model. So for us, we firstly studied what's available, like the state-of-the-art AI machine learning model, and try them on our data sets. We compared their model performance based upon a typical performance matrix, such as MAE, RMSE, and so on and so forth. So you can see the table on my right side, sorry. So we compared the training performance and the testing performance. In the end, we selected ELM as our model approach. ELM stands for Extreme Learning Machine. This machine learning model approach gives us the optimal model performance. So the next step is calibration. You build your model, proved your model has a reasonable, acceptable performance based upon the simulation data. Now let's understand what's the gap for applying this model to a real wind turbine. So we got data from the X prototype, which is a 12 megawatts offshore wind turbine from GE. This prototype has been installed in Rotterdam, the Netherlands, since 2019. After the installation, the turbine has been operated at 12, 13, and 14 megawatts capacity. So we got a couple of years of history data from this prototype. The first thing we did is comparing the real operation data to our simulation space. So yesterday during Amy's modeling workshop, one person raised a good question. The question was, okay, so can we run some physics simulation, compare against the real field data to see the difference? Will Unreal's modeling approach can help to do that, build the digital twin for OM. So this project actually is the answer to that. So we have done this. So after we comparing the simulation space, simulation data to the real field data, we found out there are two potential scenarios we need to deal with. The first one is about dealing beyond the simulation. So in my earlier slide, I mentioned we did a design of this different combination of wind condition, environmental condition. When we compare this condition to the Rotterdam turbine condition, we saw there's some discrepancy. So that means the model calibration need to address that difference. The second scenario is about the second scenario is about addressing the difference between design and the real operation. I just mentioned that this prototype has been operated at 12, 13, 14. But in our simulation, we use the GE's X physics model. The design spec is for 12 megawatts. So our calibration need to deal with this kind of uncertainty. Based upon the data comparison, we came up with two different calibration approaches to address each of these scenarios respectively. The first one is about resimulation. Once we know this difference, for example, the plot over here, the yellow dots are the real observation in terms of shear, turbulent TI, and also air density. The blue dots are from our simulation. So once we know the difference, we can rerun some of the simulation with the real world knowledge. So after the resimulation, our data sets was enhanced to include the real world situation. The second approach is about model tuning. So we are not abandoning the model we built with the simulation data. Instead, we added whatever data is available from the real world, tune the model. So after the model tuning, we proved our model performance now has been improved dramatically. So we believe this is the right way to adapt a model building from a simulation to a real world and boost the confidence to the turbine operator to deploy this model. The next task is about building the remaining useful life prediction model. So the previous thing, we talked about the model to estimate the state of the blade health at any given time. But that's not enough. it tells you what's happening right now, what's happening in the past. The RUL model will give us the ability to progress to the future, see what will happen in the future. Because the condition-based monitoring is really about predictive maintenance. You want to know what will happen in next month, next 3 months, so you can plan your maintenance strategy accordingly. So building RUL model is not easy. For the leading-edge erosion as well, a failure mode, it will not cause structural failure. What it causes is the annual energy production loss. So in this case, we defined the RUL model as how much AEP loss. So data sparsity, even like length of data, is a huge challenge to develop the RUL model. Luckily, we got the data from our blade manufacturing testing facility. They run this rain erosion test in the lab. So they provided us with the data of under different precipitation, how the blade will grow to become rough, and what's the AEP loss accordingly for different of roughness level. So based upon this data, we built a remaining useful life model based upon some linear model regression or non-linear regression. So the plot on my right side is one of the example. In that case, we compare the overall precipitation in lab test to the real weather data from Rotterdam, and we were able to create a different data sets, use the data sets to build a regression model. This regression model helps us to project to the future. And then at any given future time point, we can tell what's the remaining useful life. So this information will help us to really build the condition-based maintenance strategy. So in close, I want to summarize what we learned from this project. Firstly, we need to do anything to tackle the data sparsity challenge. Everyone in this room, everyone in the academy always complain we don't have data. But you cannot just stop there because you don't have data. Let's do everything to tackle these challenges. The data source can be from any lab testing, can be from someone's publication, can be from the turbine operation in Europe, even much smaller capacity. And of course, it can be from the turbine simulation with the high fidelity physics model. So the second takeaway is not just focus on the most advanced machine learning and AI approach. Let's think about what's the suitable approach to help you build a model and make sure this model is field deployable. The third thing is about the smart model calibration and updating. So I mentioned we were lucky to access the first HarnetX prototype in Rotterdam. You may think, oh, wow, that's so good, you have the data accessibility. But to be honest to you, we only got 10 data points, which is usable for our model calibration. So I think no matter how challenging it is, let's just think about what's your way, what's your smart to really apply whatever data available from the real world to really make your model calibrated, updated, build that trustworthy to the operator so they can help to deploy the model and implement the model. In terms of future research, firstly, I didn't talk deeply about how we build the remaining useful life because our model approach is purely based upon the precipitation comparison between Rotterdam and the lab test. In the future, we want to consider the wind speed, tip speed ratio, and the other factors, because the tip speed ratio particularly will impact the remaining useful life for the leading-edge erosion. So there's so many other factors we want to consider and into this remaining useful life modeling approach. The second perspective is about trying other remaining useful life modeling approach. We did a state-of-the-art study, but we only tried one method. So our plan is to investigate and also explore other RUL approach for this project. So thank you very much.
Okay. Hello, everyone. Thanks for joining the discussion and panel today. I'm here to talk about our NOWRDC project on assessing the integrity of offshore wind turbine blades during manufacture using advanced non-destructive examination technology. And I'd like to open it up with some recent statistics. Wood Mackenzie put out their O&M projections report, I think in October, and they had some pretty alarming numbers in there. They're projecting $4.7 billion to be the cost of all repair or blade replacement and retrofits by 2030. And then they identified they're expecting 116,000 blade repair callouts by 2030. So these are huge numbers, and this is already starting to happen today. We're trying to approach it sort of within operations through visual inspection. We're starting to see condition monitoring approaches emerge both off the blade and on the blade. And at the end of the day, that's only telling you a piece of the story, and we're trying to improve what we're calling blade health management. And at the end of the day, blades have inherent flaws in them, and I like to think of an analogy like the Dutch dams. You don't see the damage with a visual inspection until it's reached the surface, and so by the time you're plugging that and trying to prevent a leak, there's something else likely already happening. And in the case of blades, when there's damage on the surface, you're now affecting the aerodynamic performance of that component as it's rotating through the air, subject to stochastic input. So the consequences can be pretty drastic as soon as something initiates on the surface. So the goal is to understand what is the true integrity of the blade on the surface, subsurface, all things in between. And so in order to address that, we have to start in the factory where the blade is first manufactured. And that's what this research project is focused on. Is how do we get deeper information and quantitative information about the quality of a blade before it's received at site during development. And then ideally that information is then carried over to operations so that we can start deploying our condition monitoring solutions and our visual inspection schemes with that data contextually in mind. So when we're talking about wind turbine blades, they're fairly complex structures to manufacture. They're composites. These days they're comprised of fiber reinforced plastics. Carbon fiber is used a lot for the span-wise structural components inside the blade, the spar caps. They previously used a lot of woven fabrics and now are switching to pultruded carbon that are being adhered on top of one another. And if this is all a foreign language, I apologize, but it all means that the material properties are changing all the time. At the same time, these blades are always increasing in size because we're trying to maximize power capture. So it's a complex problem, and we have roughly 0 sensors on the composite materials of the blades themselves. So there's a lot of gap there to fill in and try to understand how to manage the health of these components through the lifetime. Rather than as more of a consumable, we want to treat it as an active asset and monitor it as such. So what we're looking to do here is determine the feasibility of applying more advanced NDE approaches to assess the structural integrity and quality of a wind turbine blade. So we're focusing it on offshore wind blade technologies, the geometries that we're seeing adopted more so in offshore environments, as well as the material compositions. And what we're doing is looking at new approaches that are not applied comprehensively in the factory during blade manufacturing. So it starts with looking at how blades are designed and how do these manufacturing flaws first manifest themselves into the blade. You know, when we're detecting damage on the surface using a drone or visual inspection, that's not necessarily, the physics is what provided that feature to be available for us to detect at the surface. How it initiates is not necessarily through the same mechanism. So we're working with, and I have on the next slide some of our partners, we're working with a blade manufacturer, a domestic blade manufacturer, to understand exactly how these blades are being designed for offshore and determine the key inspection areas of interest for these specific types of blades. We're working to fabricate realistic test specimens, actual geometries representative of offshore wind blades that you will see very soon out on the East Coast. And we're also working with already existing samples so that we can get our subject matter experts up to speed with the types of materials and the applications, the types of wedges and probes we need to be considering. And for the non-destructive evaluation side, we're considering both advanced ultrasonics as well as microwave imaging. And the microwave imaging has some real interesting potential when it comes to the depth at which you can scan certain features. And so on a wind turbine blade, I mentioned that there's a lot of complex materials, fiber reinforced plastics, carbon fiber, balsa wood. There's a foam core on these larger blades. On the upper right side, you can see a cross section of the blade. And as you get closer to the trailing edge, there's a foam core that's there to support, structurally support the blade. And when you're using something like NDE, you have to penetrate both the surface of the blade and sometimes the foam core to get to the feature of interest that you're trying to detect. So these are all the types of things that we're trying to figure out what we can realistically detect. And at the end of the day, we want to demonstrate this both with lab specimens, freshly fabricated specimens that represent offshore wind blades, and then take these approaches and demonstrate them in the factory. We also want to demonstrate this at site. So basically have a hypothetical scenario where the blade is manufactured, transported to site, and then there's a developer who's signing off and receiving it. So what is that QA/QC criteria? Is it the same as it is in the factory? What sort of checklist should we be thinking about developing? And at the end of the day, we want to improve these techniques for blade flaw detection, get them applied in the factory, and if it turns into something like an MRI for a blade, that's great, but we want a calibration sheet, a spec sheet that tells you where your inherent flaws are, where they're located on the blade, and then over time, as we monitor these blades in operation, we have a much better understanding how we expect those subsurface flaws to propagate and what we expect the initial damage to be. And then maybe we can apply condition monitoring at that point to predict it before it even reaches the surface. So this is our project team, led by EPRI. I'm managing the project along with John Lindberg and Brandon Fitchett. So John Lindberg has been with EPRI for over 40 years. He is an NDE expert. He's worked in all applications of non-destructive evaluation, so we're thrilled to have him on the team as a subject matter expert. He worked on the fabrication of the Sandia blade specimens as well, and some of the NDE approaches to detecting some of the initial faults that were defined by DOE. Along with John, we have Brandon Fitchett, who leads EPRI's wind program. He has 13 years of experience in blade design, system integration, aerodynamics, and operations engineering. He worked on blades at both Siemens Gamesa and Clipper, and he has a lot of composites experience. Along with myself, I got my career started at Purdue, working in sort of their aerospace program on composites, and we worked with Department of Defense to take carbon fiber and fiber reinforced specimens and understand how to detect them in situations that are mission critical. So taking those types of methods and applying them to wind energy has been a lot of fun over the past 10 years. Also on our team and in the room is Dr. Curtis Fox, who's EPRI's offshore wind lead. He leads all of our offshore wind research efforts and has over 10 years of experience in drivetrains. He worked at the Clemson drivetrain lab where they had their large dyno. And then, so that's all on the wind side. Also from EPRI, we have several subject matter experts in NDE, Sal Villalobos, Dr. George Connolly, both bring over 30 years of experience combined. And then, so they all bring in all of our ultrasonics experience. They have tons of experience in that department. And then we have Bob Stackenborg from microwave imaging. And so Bob is active in the wind industry, developing new approaches to inspecting deep flaws on blades especially. He works with a lot of the domestic production partners, and he's considered a global expert in microwave inspection. So we're looking to combine these two methods and work with Steve Nolet from TPI Composites. Steve is principal and senior director at TPI. He's located at the Warren facility, just a little over an hour south of here. and he's a global expert in design and manufacture of wind turbine blades. He's been here for the wind turbine blade conversation for decades now, and we're really excited to work with him. We have identified a domestic facility where we'll be working with Steve to demonstrate this all near the end of the project. And then Michael Lunsgaard is our wind farm operations subject matter expert. We have an end user partner, it's Dominion Energy and the Coastal Virginia offshore wind site. So we'll be working with them as our development partner and understanding how this information needs to get transferred from the factory to the site and then make sure it gets integrated into the operational strategy as well. So here's an overview of the project. We kicked off this project in mid-September, so we're now 3 months into it. We're well underway. At this time, we are identifying the specifications for our blade samples that TPI is going to fabricate. So it's an ongoing discussion because we are also in the process of receiving several specimens from Sandia. In about 2012, Dennis Roach and the Sandia wind team developed several wind turbine blade specimens. If you're not familiar with it, come talk to me. I can tell you more about this. They fabricated at least 25 or 30 samples with embedded flaws, and some of the specimens are blind, some are not, and it was meant to provide a baseline for identifying delamination, disc bonds. These are some of the damage types that you see in blades, and come up with standardized approaches through NDE. And so we'll be working with those samples to establish a baseline and establish an approach, and then the real challenge is then applying it to the realistic, the thicknesses, the different cross-sections, the different geometries and cross-sections that you find, just in particular the thicknesses of each of these areas that we'll be inspecting, making sure that we pick the right frequencies and transducers to detect what we need to do. And so our go, no-go evaluation will happen after task 2, in which we will fabricate these samples, we'll have our Sandia test specimens, we'll develop our techniques through ultrasonics and microwave imaging, and we'll have this approach demonstrated in the lab. Once it's demonstrated in the lab, and as we proceed through our go, no-go evaluation, we'll then work with TPI to demonstrate this in their facility and come up with a robust method that can be applied so that if you made an order for a new blade and you want to get that extra due diligence, that you would have this checklist and approach that you could take with you to the factory if you wanted to execute it yourself. These are the blade manufacturing flaws of interest. I'll go through each of them briefly. We have a cross-section of a blade shown here on the slide as well with the foam core, so you can get an understanding of some of the material makeups of a more modern blade. Trailing edge bonding, so as you go towards the trailing edge where it meets at a point on the right side, there's a bond line there, and there can be variations in the thickness of that bond line. There can be voids depending on how that bond line is applied. So assessing that bond line integrity in between where the two trailing edges meet is of high importance. Another bond line that's important is the shear web bonding to the spar cap. So you see that black area underneath, that's the spar cap. Where that bonds to the shear web and where that bonds to the clamshell is important. That shear web is there to prevent buckling from happening, so it's incredibly important that it has high integrity. And so we'll be inspecting that bond line. And there are many different configurations still in how shear webs are manufactured, mostly working towards pultruded carbon, but we'll be working with a few different types of materials. Delamination is very common between the plies, having a delamination occur. Also kissing bonds where you don't see the delamination between the plies, but it looks as though it's bonded together, but it's puckering, so there's actually a delamination underneath that you can't see, and we want to detect those as well. Fiber waves, so imagine you have your waves in the material to make up your profile of the blade, and as that material is curing, it's subject to heat, and it can deform, it can become wavy, and that's going to affect your aerodynamic efficiency. We would never want that on the surface of our blade. Realistically, you're just applying gel coat on top of that, but that does affect the overall integrity of the blade and performance. So we want to detect waviness in the trailing edge reinforcements. As the blade is cutting through the air, we want to make sure that's nice and smooth. Mid-span, so there can be carbon spar cap waves and bubbles. As these blades get longer, you know, it's not just a single spar. You have box spars, or you can even have shear webs. You can even have 3 vertical shear webs inside of a blade. And then there are transition regions that are taking place. So again, these are very important areas to inspect, structurally speaking. And you want to look for waves, bubbles. Bubbles would suggest that the resin, there's something in the chemistry that's not adhering the resin to the fibers. And waviness would affect the integrity as well. Overall fiber orientation, we're interested in knowing that if we can identify it. Porosity in the root section, so especially where the root bonds to the composite material, you don't want risk of water ingress there, because then the water can get inside the material. And so porosity.
Could you say that again?
Sorry about that. Siri's asking me to explain it. So yeah, you don't want too high of a porosity in your root section. You don't want water coming in through that area. We're going to come up with methods to detect that as well. And then this one is at the bottom of the list, wish list, leading edge urethane coating film thickness. So sometimes leading edge protection solutions are applied in the factory. One example is urethane coating, which is painted on the leading edge span-wise across the entire blade. And that film thickness is not really measured in the factory. So we're trying to identify if that can be done through NDE, or perhaps just apply some feeler gauges or a certain methodology to keep that consistent. Okay. These are just some examples of the test specimens that we're utilizing from Sandia. And these are some examples of the microwave imaging, the software and the types of microwave imaging we'll be doing, and we can get 3D renderings as well. So we're hoping to get into the subsurface as much as we can. Thanks for your time.
All right, good morning, everybody. My name is Murat Inalpolat. I'm a professor of mechanical engineering and working under UMass Lowell, UMass Lowell's mechanical engineering department, as well as Center for Energy Innovation. Today, I'll try to explain and give you some background on our relatively new project with NOWRDC, which is supposed to be kicked off very soon, shortly. So my talk will be predominantly on, giving you some background on using acoustics for operational blade monitoring on a turbine. I think we've already established in this conversation that blades are susceptible to fatigue and weather-related damage. And if this is an offshore turbine, because of the ultra-large scale blades, as well as other difficulties for remote accesses, etc., different environmental and operational conditions added to it, it becomes a different problem. Some of these are already, Noah gave a really good talk on different types of damages and in the form of debonding, holes, cracks, etc. And I also want to add to that is that there is a significant cost contribution for an O&M. Just to throw a number there, it's reported as 12% of the overall O&M costs for an onshore turbine, and there are also highly cited reports now coming out there for offshore, stating that it will be even higher for offshore turbines. Our motivation comes from the fact that currently, as far as we know, turbines do not necessarily have integral solutions for operational blade monitoring. And we are working under this project, we are working on a distributed sensing approach which utilizes acoustic information. Lots of different techniques have been tried out by researchers, including us, and most of them have been successful in the lab environment. Some of these techniques include vibrations, acoustic emissions, ultrasonic, fiber optic-based techniques, as well as photogrammetry, which is an optical approach. And again, these perform well in the lab, simulated conditions, as well as in lab. But in real operation, when the turbine is operational, most of these are not really successful just because they either have limited damage detection rates, and thus you need so many of these sensors there, which is not feasible, or they have cost prohibitive or effectiveness is limited. And thus, we believe there's a significant need for a feasible condition monitoring approach for turbine blades. So our objective, in short, is we would like to be able to provide or help provide a low-cost but highly capable blade monitoring solution to the industry, which will hopefully avoid total blade replacement and convert unscheduled, extremely expensive maintenances into scheduled and much less expensive maintenance schedules. In this project with NOWRDC, our main objective is to further develop and demonstrate the technology we've already developed and show the capabilities in an offshore environment. Our solution we provide, as I mentioned before, is acoustics-based. So you're looking into a schematic where I'm only showing you a blade. Those lines inside the blades schematic are the shear webs that Noah was describing a moment ago. They support the blade's hollow composite structure. And we see these, a blade is being a number of cavities separated by these shear webs. And we are using one sensor per cavity of a blade. And these sensors are wireless for data transformation. But they are still powered via wires in this configuration, though we also have an upcoming project with a completely wireless approach that we are working on. The system entails in-blade sensors as well as a single external blade sensor, which is down tower mounted on the tower itself. It's magnetically attached there. And we like this approach because it's a relatively low cost, no contact or non-contact technique. It's acoustics-based, non-destructive. You don't really cut or do anything on your blade. It just gets mounted inside the blade. Relatively easy installation, and the approach is predominantly data-driven. There are different aspects to this project that we've been working on and we will keep working on. Today, I just want to give you the main theme here is the passive acoustic detection. Though we've been working on active detection, we definitely worked on aeroacoustics, machine learning, environmental effects, reliability, etc. So if you look at this slide, the top part of the slide is meant to show you the healthy. It's a schematic for an airfoil, 2D airfoil, representative of a blade, separated by a shear web. The line through is the shear web. And then, again, schematically, I'm showing internal microphones. Of course, they are not just sitting inside the blade. They are mounted. I'll show you how it looks later on. But the main idea here is that as your blades are traveling through air, they couple with the wind flow. And that sort of gives you a certain background noise level. And your blade internal sensors are expected to pick that up. And if there is any deviation to the blade structure during operation, now your airfoil, the blade, will be coupled with air a little bit differently, creating some acoustic aberrations. And our sensing methodology is supposed to pick those up. Just to give you a little simpler analogy, imagine you're driving on the highway and then you'll be hearing some road noise and wind noise, obviously. But if you were to crack open one of your windows, you will start hearing a lot more. And this idea is based upon that fundamental idea here. There are, analytics and other studies that we've done, but I just want to briefly mention about the experimental parts of our investigation so far. It has been in 3 different phases. In the first phase, we've done some work at a lab scale with controlled acoustic excitation. What I mean is we've used blade sections in wind tunnels and have done some testing. In the second phase, we've done some full-scale blade investigations with the help of Massachusetts Clean Energy Center's WTTC, where we were implementing our acoustic system on blades which were getting tested for fatigue. And then here the excitation, mechanical excitation is controlled, but the acoustic excitation, which is coming out of that, is not really controlled. And in the last phase that we've been studying so far is a full-scale wind farm testing on a single turbine. And this is definitely uncontrolled under non-stationary acoustic excitation. Again, skipping the first and second phases and simply want to briefly talk about the phase 3, which is wind farm on a real turbine testing situation. I was trying to show you inside the turbine blade where you can see where a sensor is attached. Actually, these sensors are chemically bonded on a shear web close to the neutral axis, so they are affected by the rotational effects, minimal, at least based upon our understanding. And the sensor has a cable that comes from the hub, from within the hub. They are powered. These are all DC-based systems. There's no AC that we are bleeding inside the blade. It's all DC. And then data is transmitted inside, down to a box, which is down tower on the ground or somewhere close to down tower, and is transmitted to the cloud using a 4G LTE cell phone system. A few pictures and a little bit of a story about our recent implementation at NREL. This is the GE DOE 1.5 megawatt machine. Most of you may be familiar with this machine. We've implemented the sensor, and we were trying to run a test campaign for 2 weeks under our Department of Energy funded project, and we ended up running this for more than 5 months successfully with no issues. Collected about 70 gigabytes of acoustic information, which translates into about 600 hours of acoustic data. Again, no issues. And this has recently been decommissioned. We also have another system going in Texas at a company's wind farm, successfully collecting information. Again, the left-hand side picture is NREL's 1.5 GE DOE machine. In the center picture, you're looking at two boxes there. The box at the center point is our box that transforms the AC power coming from the hub, from within the hub to DC, which our sensors needed. And then over on the right-hand side, the picture is showing you the down tower box where all this data is being bled down to. Schematic indicating where these sensors were sitting at the NREL implementation. In our language, MNA, those red boxes, means it's a sensor. And one sensor is about 3 meters, and then two others were implemented about 18 meters from the blade closeout section of the blade. Over on the top right-hand side, you can see one of our sensors attached, bonded onto the shear web. And then on the right-hand side, bottom right-hand side, you can see the power cable, which was tagged along the shear web using, again, chemical bonding, though we tried other types of bonding on shear webs in the past. So this project so far until this point has taken a number of steps we worked through. We essentially started in our lab at the university using a composite box and trying if the sound were to pass through a box, can we detect that, all that simple stuff. And then we worked our way up using subscale turbines, blade segments, WTTC testing, full-scale blade, not really in operation though. And then we recently tested on, in a wind farm. So how this connects with our upcoming NOWRDC project is that we have done some studies and investigations, as I mentioned, but we have not shown or demonstrated this technology in the offshore environment. And actually, this NOWRDC project is essentially going to be helping us try this technology in offshore. So one of the main things that we are going to be trying to do is system development and testing in an offshore environment using an offshore turbine off the Virginia coast. And then sensor ruggedization and testing for vibrations, thermal, humidity, and lightning, which are supposed to be expected to be problems in offshore environments. And also, we want to work heavily on commercialization aspects of this. One can find out the tasks on the timeline. You can see the go, no-go point decision. But the main tasks are actually building the hardware, identifying the vendors, procuring the parts, and testing on 1 to 2 turbines, Dominion Energy offshore turbines in Virginia. Analyze the data and report out the results along with some commercialization tasks. Here's our team. The core team is from UMass Lowell. I'm the PI of the project, along with my co-PIs, Chris Nizreki and Jan Luo, both from UMass Lowell. We will hopefully have a really close relationship and collaborations with EPRI, who can, an agency which can also mentor us for commercialization, not only the technology part. Of course, NOWRDC is our main sponsor here, and hopefully we'll be collaborating with them closely. And finally, NTS is our collaboration for lightning strike testing of our sensors. Last but not least, for commercialization, here's our ideas at this stage. At the end of this project, our technology is supposed to be coming up to TRL 6 to 7 levels. Our collaborations with EPRI is going to be critical in taking this technology to there, hopefully. We also have a WindStar, Wind Energy Research Center and Center for Energy Innovation at UMass Lowell, with a lot of companies in a consortium, including GE, etc. Those companies are expected to be also helpful in mentoring us for commercialization. Potential customers include equipment manufacturers, blade manufacturing facilities, wind testing facilities, and potentially later on wind farm operators and major OEMs. Lastly, I'd like to thank all of the sponsors that has helped us bring this technology up to this stage, including the DOE, NSF, Mass Clean Energy Center, and UML's WindStar, and now National Offshore Wind Research and Consortium Development Consortium. Thank you very much.
Morning, everyone. I'm John Garrity, co-founder of TagUp. We're a company whose expertise lies in machine learning practically applied to industrial systems. Happy to describe our work, collaboration between TagUp and EDF Renewables in the United Kingdom, and thankful for our sponsors, NOWRDC, Massachusetts Clean Energy Center, and the Department of Energy. The core of this work is in supporting O&M for offshore wind turbines, specifically to identify critical events that result in material O&M cost. What does that mean? That can be specific component failures that require intervention. That can be planned maintenance as well. How do you optimize for that planned maintenance? Very specifically, we're working at 2 offshore wind farms in the UK. These are Teesside and Blythe. They are a 28 2.3 megawatt Siemens turbines and 5 8 megawatt Vestas turbines respectively. The challenges that the O&M team face here are looking at a lot of different factors that come into play all at once when you're making maintenance decisions. There's unique to offshore wind, the maritime operations, so you need to consider everything from the sea state, are you actually able to access the turbines, ship and crew availability, who can actually do the work, the planned and preventative and condition-based maintenance that can be done, and then finally, what inventory do you have? What parts are available? And it's a very complex planning task, considering across all these different dimensions, to identify what actually needs to get done. Our work is to apply by taking existing data, primarily SCADA-based data, but also work order management information, weather data, sea state, for example, ship and crew availability, and identify what should be done, what is the order of operations for maintenance task, in order to reduce O&M cost overall and thereby improve LCOE for offshore wind. The principle behind some of these methods that we are applying are what are called time to event models. So prevailing art in offshore wind operations and very broadly, we actually started in the utility sector, regulated utility sector, and the best in class we've seen is related to sort of asset health scores or condition scores. Where you look at a lot of different factors that come to play, and you can normalize those factors such that you get an understanding of the overall health of the asset. That allows you to rank order the assets and prioritize them for maintenance and operations. But the challenge is it's not especially specific, right? What is the expected failure mode? What parts should be taken? How much should you prioritize one asset versus another? And there's some refinements that you can make to this. EDF, before our work, is looking at, for example, what is the energy generation from a specific turbine, what is the lost power generation, right, with the goal of maximizing what they call energy-based availability. That is to say, can the turbine generate power when the wind is blowing or not? The disadvantage of these approaches, I often give the analogy, it's like your doctor telling you you're 80% healthy. Great, I'm healthier than, my wife's healthier than me, I'm healthier than my grandmother, but what do I do? And the advantage of these specific approaches is that you can say, okay, the probability they have a heart attack is, in the next 5 years is 3.5%. All right, I can work with that. Now I know how much I'm willing to improve my diet and exercise versus maintaining the status quo, which is very comfortable. And the same is true for specific failure modes we're looking at here. Our phase 1 work under this collaboration, we're looking at what we call curtailments, which are EDF's definition of unplanned downtime. And I'll give more specifics as to what that entails. In phase 2, we've looked at specific failure modes. It's a harder problem because fundamentally these methods are driven by available data. You need examples of the events in order to predict specific failures. And there are many more examples of unplanned downtime writ large than there are of, say, yaw motor failure. But through phase 2, by expanding the scope of data, we've been able to look at very specific failure modes in addition to this broader definition of an event. What you see here, and I think this is a PDF now, yeah, so no animation, but the principle is that you're looking and trying to predict the time at which an asset will fail. So on the horizontal axis, you have time in weeks from an initial period. You have a predicted time of failure for the asset, which is the orange line, and the actual time of failure, the red line, and a confidence interval is provided in the shaded area. The specification of these models is what's called a hazard function. We derive a hazard function. This has a long history. Originally it was actually used in drug trials to determine survivability of patients, and is used in many different applications, including life insurance and the like. What we've been able to do now with improvements in available compute, in model specification, is take huge corpus of SCADA data and work order data and combine it all in order to predict when an event will occur. In machine learning, this is a supervised learning approach. We have examples of the event. And as time goes on, we get more and more information, which is not represented in the absent animation, but the basic idea is that the orange line's position shifts as you get more information. Again, the analogy would be, as the doctor gets more information about my respiratory rate or my pulse, right, and activity levels, you can better coordinate the time, the estimated time, with uncertainty, when I might have a heart attack. And certainly if you saw arrhythmia or something to this effect all of the sudden, that might indicate a much higher probability of this event. So same principle here. Again, when we're starting in the initial work with EDF, we're looking at curtailment writ large. Okay, in terms of data sources, which I want to cover on just briefly, there are a number of different relevant data sources to be considered, and a big part of this is making sure you have all the different pieces together. We've been very fortunate now to expand the scope from the initial 28 turbines at Teesside to also include Blythe, but now several hundred turbines of the same type. So we've markedly increased the scope of the data through phase 2, driving much higher levels of accuracy. The same types of data apply across the board, though. These are principally SCADA type data, so all the measurements, you're getting alarm codes from the turbine, you're getting power production levels, work order data, so what replacements have been made, what parts have been replaced. There's one piece here that's included as well, in addition to the SCADA tags, the alarms, and the work orders, which are financial data. So a big part of the equation is not just predicting when an event will occur, but what should you do to minimize cost or to maximize production? And so looking at replacement part cost, looking at crew availability, and do you need to incur overtime expenses in order to perform a certain action? Is it worth it? And so that's the sort of the fourth leg in this data table that we're using in order to make these recommendations and optimizations. Okay, briefly in the data pipeline, this is a big part of our phase 1 work. In phase 2, we now have, we went from basically static extracts of data. Phase 2 is now online. So we're getting updating data every day from the wind farm. This is informing online models that are making calculations on the fly of probability of curtailment now again to start. But more broadly, now we're looking at specific failure modes. The 4 failure modes we're considering at this stage are what are called delta module failures, a converter, the coolant system for the converter, yaw motor failure, and the pneumatic system in the nacelle for working with yaw. So those are the 4 specific failure modes, and we've been able to, with a much increased scope of data, make accurate predictions of those specific events. Curtailment I'll talk about again briefly. This is what we did successfully in phase 1. But what's nice about these models is you can define the event of interest. And so in the initial work, we're looking at curtailments, which narrow down on the power curve is where you have wind above the cut-in speed, below the cut-out wind speed. You have active power of 0 megawatts or less, and you are not waiting on the grid operator. You are having power demanded, but you cannot produce it. That was the definition used in phase 1, and again, that's now been expanded into specific examples of failure modes in phase 2. okay, what does this look like practically in terms of the output? You can see here, these are probabilities of the event over the next maintenance window. The red lines are the recommended interventions. Those are based on a calculation, an economic calculation, including all the different considerations I mentioned, and the probability of the event occurring. The event is the green line. And so I want to give examples of false positives, true positives, and false negatives, because when you look at calculations like this, I often say it would be very easy to predict all the failures, right? You just say a failure is going to happen all the time. Every time there's a failure. But that's not useful because there's a cost to making that prediction, right? You're not going to take an intervention if you make recommendations, it's going to fail all the time. Conversely, you could incur no false positives by making no predictions of events. And that's effectively the status quo, right? They're responding to downtime events as opposed to proactively making decisions around them. And so practically, the sweet spot is in the middle. And that's based on an economic calculation looking at the cost of false positives, the benefits of true positives, and the cost of false negatives, and combining them in order to determine what's the right threshold loosely for us to make decisions around O&M. And so again, you can see how this is manifest in an example here. In the first one, the intervention is recommended, but there's no event that occurs. So if an intervention is taken, there's a cost to that intervention, and there's no concordant benefit. In the true positive, there's a sweet spot before the event, not so far in advance, but close enough to the event, which is that shaded area. And that's where the benefit is recognized. And then finally, false negative, where you don't make a prediction of, or suggest an intervention, but a critical event does occur. There have been a few key outcomes from this work. I want to, in summary. The first is related to reduced O&M expenditure. In phase one, we and EDF identified depending on the asset, 4 and 10% reduction in O&M cost associated with a benchmark that was established by EDF. The second is one of the things we're exploring in phase two is related to inventory management. So it's hard to predict very specific failure modes for a specific turbine at a given time. That's a really hard problem, right? If you have a lot more instrumentation, you can do it, but statistically with the data available, it can be hard. When you aggregate, though, across multiple assets, it becomes an easier thing to do. The analogy I give here is like picking stocks, right? It's very hard to pick a stock that's going to return you 100x. So you buy into a portfolio, right? This is what venture capitalists do. They buy a portfolio. They expect maybe 1 out of 10 to generate a 10 or 100x return. And the same principles here. Not all the turbines converters are going to fail. Maybe one will, but you need to know how much inventory you want to maintain so that you can replace it when it does fail. And this is becoming more pressing now. Talking with EDF and other partners we have, lead times for some of the replacement parts are really increasing. For example, for these converter failure, for what are called the Delta modules, as I mentioned, the lead time used to be able to get them overnighted. And now in some cases, it's been 6 months for them to get a replacement Delta module. That's a lot of downtime. And so by using these models, you can effectively predict, again, for the specific failure modes we've looked at, what are the right levels of inventory to maintain so that you can reduce that downtime out of the future. I think I'll pause here. We're excited for phase two. Again, we're doing online machine learning for the specific failure modes. We're looking at a large number of assets, and I know there's no Q&A now, but happy after the panel to take any questions. Thanks.
Okay, hi everyone. It's good to see you all. And I just want to thank my panelists for the really compelling presentations. This is exciting work, and it's really wonderful to get caught up on what you all are doing. And thank you to the audience for coming today and for sticking with us. This is the last presentation, then we'll go into Q&A. There are a lot of people that contributed to this project, and we're getting to the end of a 2-year project. We're in the middle of wrapping this up. The official title is Optimal Sensor Placement for Physics-Based Digital Twins. One of our close colleagues, Hamid Ibrahimian from UNR, is in the audience. Hamid, I want to thank you for all the work you've done here and bringing the drivetrains into this project. Really want to thank Kevin and Mel and Corey and Carrie Hitt before Kevin, and Christine Sloan, who's been the project manager for this on NOWRDC. Sherry, I want to thank you and your team, Mark Kozak, and Dan O'Connell, and the vision that you brought to this originally, because it was really the Bessie team that created the ability to instrument these turbines, and it was the NOWRDC team that has created the ability to take this work beyond that. And then we have an Innovate UK grant that came in as part of this work as well. So by pulling together over multiple years, and you see the idea for this project goes back to about 2012. It was originally a DOE Topic Area 1 project. And sort of through the years, the same team has kept track of this thing, and we finally have succeeded in instrumenting Block Island and monitoring this for a year. We're about to start monitoring CVOW. We've installed instrumentation there, and we've also been monitoring the Leavenmouth demonstrator turbine with our colleagues at the ORE Catapult. So thank you to everyone who's been involved. As we're wrapping up this project, hopefully we'll be debuting this more publicly and talking about this in 2023 to try to really figure out how to make the results of this project more accessible to the wider community. So Block Island, as you all know, is the first U.S. offshore wind farm, 5-6 megawatt turbines in state waters. Another colleague I want to thank is David Ciacchetto from CRMC, Coastal Resources Management Council of Rhode Island. They wrote the lease for this turbine and specifically have a clause in the lease where research needed to be done on these turbines. And so that was essential, that this was written right in from day one to the lease. Also want to thank Mass CEC, Nils Bolgan, has really been supportive of us through the beginning of all this and has really developed a strong relationships between the state of Rhode Island and the state of Massachusetts, and there are conversations now also with the state of Virginia. The instrumentation, the title of the project is Optimal Sensor Placement. When we started talking with Jens Gengenbach at Ørsted about this several years ago, he said, please just don't put 600 instruments on this turbine and then don't tell me you don't know what to do with the data. He said, I want you to put as few instruments on the turbine as possible, and then I want to know what every single instrument is giving us. And that's kind of been our approach for optimal sensor placement. And we have all sorts of methods that we've been publishing on optimal sensor placement, but there are also some very practical limitations and constraints to what is optimal. It's too expensive to put sensors under the water. These turbines, we're putting them on as a doctor's kit. We're all retrofitting the sensors. We can't really put them in the nacelle. We can't put them in the blades. We put them on the tower. And we essentially create 3 or 4 levels of accelerometers and then 1 to 2 levels of strain gauges. It turns out we're finding this is enough to give us the vital signs of the entire system. We can find 1P, 3P, 6P, 9P, 12P frequencies coming down into the tower, filtering in. We can find mode shapes, natural mode shapes as they're interacting with the different frequencies. We have very high quality sensors. This was designed by the Norwegian Geotechnical Institute, sampling at 50 hertz. They're in fantastic condition, wonderful data acquisition system. So with the support of our sponsors, we really developed a first-class instrumentation system that's going to last for a lot longer than the duration of the project. Now, interestingly enough, this all happened during COVID, and so we were counting on the Norwegian Geotechnical Institute to come over and install the sensors. This is my colleague, Babak Moavani, and at the beginning of the project, I remember Babak was all excited to go out and install the sensors on the turbine, and I said, Babak, that's not what we do. You know, we have to leave that to the professionals. But COVID comes, NGI can't come over to the United States, and so Babak and eventually Chris Baxter from URI get trained up and buy themselves $4,000 of PPE and go to Mass Maritime for a week, and ultimately went out with the GE technicians and the Ørsted technicians and installed the sensors on the turbines. We've really appreciated the ability to do that, to be on the ground, and so at the professor and PI level, we've been hands-on this project. You can see we have automated systems ID results for over a year. This is not something I'm going to be getting involved in very much in this presentation, but the idea that we have a year-long live data stream. And we are making these very clear observations, for instance, of fore aft frequencies. You can see in the red here, that's the parked frequency, and then in the blue, in the fore aft direction, the frequency of the turbine actually stiffens because of a relationship between the centrifugal effects on the blades, because of a gyroscopic effect of the rotor, and we're observing this very clearly. And then also from the frequencies from the side-to-side direction, which you see on the right-hand side there, are fairly stable. Again, damping ratios, we know that the damping ratios in the fore-aft direction on the left are critical to really understanding the fatigue life of the turbine, and so it's feeling really good to be able to get these damping ratios and to understand them and to think more closely about how we're using them in design. And again, on the side-to-side, we see that the damping ratios are lower, down around 1%. One of the things that Bessie and BOEM and NOWRDC have been interested in are also the monitoring of tropical storms. And so this is Tropical Storm Henri, I think from earlier this year. And talking about sort of when we can see when the power goes out, we can see when the peak loads are, the peak accelerations, we can see when the turbine is parked. And what we'll notice in all of this, and this is just a tropical storm, this isn't a Cat 5 hurricane or something like that, but the loads during the tropical storm are substantially lower than the loads during operation. Clearly, when the turbine is operating, you're catching the entire actuator disk of wind, right? And so the loads are very high at that time, and then plus there's the back and forth from the fatigue. And so a lot of the highest loads that the turbines are seeing are during operation. This really means to us, it validates for us that fatigue is the driver of turbine design. It's the thing that we need to be watching out for. And then there are times when the storms make a big difference. But generally, when the turbine is parked, there's so much less area for the wind to be blowing on. It comes down to more of a sort of a component by component level phenomenon and not an entire system phenomenon. You can also see from the 4A amplitude spectrum that we get the first modes, we get the 3P, we get the 6P. And we're able to see all of this very clearly when the turbine is parked. The second structural modes generally get sort of mixed up inside the 6P and the 9P range. But when the turbine is parked, we can identify those modes as well. And so we're learning more and more about how to read the turbine. And really, we think about this as monitoring the vital signs of the tower. And so originally, we weren't sure how much we were going to be getting in the tower, but the amount, whatever is happening anywhere else in the turbine finds its way into the tower, and we can monitor all of this also from a high frequency point of view. And we're very excited to be partnering with our other colleagues in the future to be thinking about also monitoring the blades, monitoring the drivetrain, monitoring the tower, monitoring the foundations, and watching to be able to capture the entire system. And so again, you can sort of see system ID results. We can see very different mode shapes between when the turbine is parked and when the turbine is running. This is again still during the tropical storm. And you can see the frequency and damping evolution during the storm from going when the turbine is operational to when the turbine is parked. These are the second mode shapes. And then this is the frequency and damping evolution also during that tropical storm. The vibration amplitude we're seeing again is rising, and then we park the turbine, and then we can see the vibration amplitudes again going down. And then finally, to just acknowledge the range of people that are involved in this project. It's been a tremendous team over the last several years. We have our students and our researchers. We have all of our colleagues at Ørsted, to whom we're tremendously grateful. They were working with them on this turbine and also on another turbine in the North Sea, advancing these Bayesian methods, these Bayesian inference methods. We're very much indebted to our colleagues at GE Renewable Energy, who've been instrumental in getting us out to the turbines and helping us understand how to just getting back and forth to these turbines is a big deal, and then making sure that we have the right data. And then all of our co-PIs from URI and from CRMC, from UNR, from NGI, and from NREL, Amy Robertson and Emmanuel Brandlard have played a critical part in this project, helping us situate this piece of work inside of the larger OC projects. And we have a report coming out that sort of benchmarks the work that's going on Block Island with what's been done to date and sort of what do we see as the next steps in terms of making this open access data. And then finally, once again, we want to thank Bessie and NOWRDC, DOE, and Mass CEC for the support. So thank you very much.
Thank you, panelists, for an amazing amount of information in a short period of time. Really exciting work, and we have some questions coming in. Remind everyone to use the Slido app to submit questions. We have about 40 minutes for questions, so please send them on in. So I will start with kind of a general, this one is not directed to anyone, so anyone that would like to take a stab at it. How does the owner and service provider of a wind farm use the technique you are proposing to inspect hundreds of wind turbine blades for defects? Is this scalable?
I'm thinking potentially this is a question for me. We think that it's scalable. We don't have the experience to tell you that yet it has worked in a wind farm level or hundreds of turbines. Our experience so far is on a few turbines, but the technique itself should be scalable.
I'll add a comment on the blade QA/QC as well. We're looking to keep that as a rapid test that could do like V&V, maybe 30 samples, something like that. But the scale at which you're making blades is a bit slower than that. So I think over time we'll try to speed it up, and as the technology evolves too.
Excellent. And for Dr. Song, in your data model, do you consider the influence of other turbine issues that can influence the performance? For example, pitch misalignment error.
Sorry. Okay. Yes, there's so many other confounding factors that will definitely affect our model performance. So I mentioned the two future perspectives. Actually, the third one will be decouple those confounding factors from the model performance.
And again, this one is not directed to somebody, so if anyone would want to answer, that's perfect. How do you isolate that the possible root causes for the underperformance of a turbine is due to the leading edge erosion by looking at SCADA data?
Maybe that's for me. So actually, there's one critical step during our model building is a feature selection. So I mentioned in our simulation data, there are about 54 variables we can use. In the end of the day, we are not using all of those. We use some feature selection method that help us to down select about 8 to 9 key variables we can use. By doing this, we believe we can kind of differentiate other impacts from other factors. So it's not purely utilize all the 54 factors and then build this machine learning model. Hope that answered the questions.
Does anyone else want to contribute to anything along those lines? This is for Tag Up. What kind of limitations exist with predicting failure modes of gearbox? Example, gear scuffing, and other components by only using just 10-minute SCADA?
Yeah, it's a good question, multifaceted question. I think the first, again, in our approach, we need examples of the events. So first and foremost, there need to be labeled examples. So in the case of gearbox, if you're looking at scuffing, to my knowledge at least, and I'm not a deep expert, but in the SCADA data we have, that's not captured as an error code. So we would need some other representation of that event occurring in order for us to predict it. The second part of the question was related to what is the sampling frequency of the data, right? Most commonly, we're looking at 10-minute sampling. So you basically have, even if the data is captured at a much higher sampling frequency, it's basically bucketed into 10-minute intervals. And you do lose a lot of signal there, unquestionably. There's other methods that are used in order to make the problem computationally tractable, where you're basically taking statistical moments or other estimates of the underlying data. And I think there is much information signal lost in that. And the question is, how do you balance the volume of the data with the signal that's being lost? And I don't think that's a well-solved problem, certainly not by us.
For Dr. Hines, was the turbine shut down in the storm because of increasing wind speed or increasing vibration?
It was increasing wind speed. It reached the threshold.
And for UMass Lowell, how are the proposed monitoring systems different from existing products, from Sensoria, Ping, Polytech, et cetera, that are already in service?
That's a good question. Thank you. Ping's product is only an external sensor attached down tower. As far as we know, they are not been doing blade internal sensing. And then Sensoria has a recent product that came out. They have a single microphone at the root of each blade. Our approach is distributed because we think that the blades are waveguides, acoustic waveguides. But if you only sample that waveguide at the end of the tunnel, so to speak, then you might be hitting one of the blind spots of that blade acoustically. We've shown that computationally, and thus our approach is a few sensors distributed inside the cavities onto the shear webs, which is also tagged along with a blade external sensor for understanding the environmental noise and capturing and differentiating them. That's the main difference, I'd say.
Thank you very much. And this question, I'm really interested in the answers, and I think everyone can contribute their perspective on this. How do you see your work applying to floating turbines, or will it apply to floating turbines? Start.
Sure, yeah. So as I mentioned in my presentation, the technology we built is a framework technology. So the methodology basically really leverages the physics model to generate more data and then combine with whatever available from the real world. So we can build and deploy a model. This methodology definitely can be applied for floating. We just need to use a different physics and a different machine learning model.
At least in our case, we've tried building models that apply across different turbine types. So building a model that's based on common features or common inputs between a Siemens 2.3 megawatt turbine and a Vestas 8 megawatt turbine, for example. And the model performance is actually inferior to models that are trained and developed only on models of a specific type, even if it's a smaller number of turbines overall. So I expect, while the models in the same way as just mentioned are applicable to any asset type, I expect that you would train models specific to floating wind turbines.
Yeah, for our blade monitoring approach, I think the answer comes from, in fact, two different aspects. One of them is our approach is based upon cellular data transmission, where you can monitor these turbines from everywhere on the world. And that may have some limitations in the future, depending on the location, obviously. But number two, regardless of the turbine type, we believe that there is always going to be some form of a controls and monitoring approach and some form of a box to collect all these signals. And as long as you have that, I think our system can be tagged along with that controls box, regardless of the turbine type.
The goal of our project is to understand blade quality. So as you're moving into a harsher environment, having that understanding at an earlier point in time is advantageous, coupled with online condition monitoring and resident drones. That would probably be the scenario with floating, ideally.
We're confident that we could apply our system to a floating system. We just need a floating system to work on. And I think that one of the issues we're working on right now is that a lot of our model updating, so we do two things with digital twinning and model updating. Our idea of a digital twin is you begin with a physics-based model, you model it, then you get the results. Then you measure what's actually going on in the real world, and then you use our Bayesian inference methods to update that model. And then the updated model becomes the digital twin. So the question number one is, what are the parameters that you update? Do you update the stiffness? Do you update the soil conditions? There are a bunch of different parameters that can be updated, and we'd like to be updating ones that are most consistent with the physics of the system. The second thing that we can do with the Bayesian methods is that we can estimate the inputs. So can we actually estimate the shear forces, the thrust force at the nacelle? Can we estimate the wave loads? And so we need certain numbers of instruments in order to be able to estimate these parameters independently. And I think that one of our goals is to start to develop inverse open fast and other physics-based, multi-physics-based models as inverse modeling platforms. And I think that's kind of the future. So I think that we won't just be doing structural updating in the future, we'll be doing multi-physics updating. And then multi-physics updating is exactly the kind of platform that one would need to be thinking about modeling an entire floating system. And so again, I think there's a lot that we can learn from how sort of both the low frequency and the high frequency travel of all of the different waves throughout the entire turbine system, and to be able to apply that to floating is completely realistic.
That is awesome. I remember one Siemens Gamesa conversation or presentation. They talked about the project certification or the turbine certification, et cetera. Once you take that turbine and take it off of a fixed foundation and put it on as a floating, that negates the project certification. So you have to kind of relook at all that. So there's a ton of challenges ahead of us on floating. The other thing, Eric, you mentioned on the Block Island lease, it was very fortuitous that I always get the initials backwards, but CRMC wrote into the lease that research had to be allowed. This was true also of the Coastal Virginia Offshore Wind 2 turbine lease. It's actually a research lease offshore Virginia, so that gave us a lot of study power. But we're hoping in the future projects will allow instrumentation from the start built into it, because it's just going to inform because a lot of the standards we can't just adopt from Europe because they don't have hurricanes in Europe. So it's a real challenge and a real problem. So a pitch to the Ørsteds and of the world to instrument those turbines. And the questions kind of jump around as you like them. So I'm going to have to go back to the top. I think this one has not been asked yet. Is it truly possible to create a digital twin using SCADA data without having access to important aerodynamic and structural properties of the blades? Not directed at any particular.
I'm happy to address. I mean, the short answer is no. I think you need certain information. You certainly need to understand the structural properties of the system. But there are machine learning methods that throw out all the physics and just monitor phenomena. And I think that's something where there's a question about how far can you take that. And I think that several members of the panel have demonstrated you can take that quite far. Where we think the combination of all of this is that if you have an entire wind farm, if you can instrument a couple of turbines really well, and then you can use transfer learning and machine learning with the SCADA data on the other turbines, then there are real possibilities to start to cross-correlate. And at that point, it becomes important to have high-frequency SCADA data. So once every 10-minute signal is a very different signal than something at 10, 20, 50 hertz. And so we're very interested in the next phase of our work on this hybrid physics-based machine learning, and we think that that's important to maintain as we start to monitor and scale up entire wind farms.
Yeah, I guess I'll just reiterate that the digital twin doesn't have to be the whole asset. It's what you define, and so there are opportunities, and there is AI already being applied in certain spaces. And so the fact of the matter is it's a complex multi-physical machine, so I don't know. With the stochastic input coupled with it, I don't know if we'll ever get there with the whole turbine. Maybe.
Yeah, I think for some of the projects, we prefer to use SCADA data because it's available remotely in the cloud. For high-frequency data, if you want to access it, you need to get access to the turbine, get access to the controller. So just because of the advantage of cloud access, we develop a machine learning digital twin model based upon that. But as both of the panel mentioned, for some other structural failure like a crack or other failure modes, it's basically impossible to build a model to detect those based upon 10 minutes SCADA data. You have to use high frequency data. I don't think this is exclusion. It's really about to figure out what's the right method for the right problem.
Go ahead.
Just one other comment on that is, there's a lack of standardization in the overall data taxonomy of a wind asset. I was just having a conversation yesterday with a colleague. Is it a pitch bearing? Is a blade bearing always the blade pitch bearing? And the answer is yes, but there's all this terminology that still varies across the industry. And I think standardization in this space in particular would help accelerate the maturation of things like AI and digital twins.
And I think that one of the things that we're seeing is that it would not be a heavy lift to include the kind of data that we're recording at Block Island and CVOW eventually as SCADA data. It's not expensive. It could be industrialized. It could be done, very efficiently. And I think that the question that's sort of coming up is, as we're modeling the entire system, we've often sort of thought about what's going on down below, and the structure and the foundations is relatively inert or even rigid because the turbines have been smaller. As the turbines grow larger, there are, like I said, there are all sorts of signals that you can pick up that allow you to help characterize the entire system. So I think, there's an opportunity if the OEMs were interested in improving SCADA data systems and directing them in certain ways to further the diagnostics.
Yeah. I really like that point. So we're talking about the OM roadmap. It's really what's available commercially today. Let's use that. What's in the research phase, different TIL level, that's our tomorrow, maybe the day after tomorrow. So that builds us our roadmap.
This isn't really a question, just an observation, that the 15, you mentioned the larger turbines, but the 15 megawatt large turbine fleet is new, and the industry is fairly inexperienced with these turbines. And we've heard in a couple of HSE health and safety conversations the concern about how these will perform, and of course then for my agency's perspective when the technicians go out there. So that's why we super encourage all this research. Any efforts to build on this work for O&M of DC collector stations and other transmission components?
Okay. I'd like to pick up on something you just said, first of all, Sherry, and I really want to echo what Walt Musial said yesterday, that we're at a time in this industry where we really have to think hard about, do we continue to grow and grow and grow the turbines, or do we industrialize? It's a lot more important right now that we industrialize. If we're thinking about going beyond 15 and we don't even have experience, and then we go to 20, and OEMs are concerned about their own financial viability and continuing to sort of grow like this, who is it serving to do all of this? And at some point, you put 20 megawatt turbines, we're going to have to start putting them further apart. You can't just put them right next to each other in the wind farms, so that they need a certain amount of area to actually capture the energy. And that also doesn't seem to be a conversation that's happening publicly. So with all of that said, and understanding that we need safety systems and we need supply chain, and we talk about the need for reliability and visibility and all these things, if we're always chasing this, there's got to be some point where we're big enough and we're ready to industrialize. And I guess I would say at the same point in the grid, a lot of the inference methods that we're using, a lot of the physics-based work, this also applies to systems in terms of how we model the grid. And this is something that we're working with colleagues to develop. How is it, what's the best way to measure the grid and then to keep track of it, particularly from a stability point of view and from the point of view of starting to understand these very large injections into the grid that we're planning that have never been contemplated before.
Anyone else? And I would add to that, how do you keep up with the training of the workforce when, as you said, do we keep up in the technology, or when is it time to stop and industrialize so that we can get a well-trained workforce? Because there will be incidents and incidents and incidents if we do not have a well-trained workforce. So those are important questions. Are companies adopting IEA Wind Task 33, Wind Farm Data and Reliability Assessment, Wind Farm Data Collection and Reliability Assessment for O&M operations? Oh, optimization, I'm sorry. Does anyone know? I don't know. Maybe Eric, for you, results from Block Island, I believe, went up to 2.5 Hz. How much information do you expect at higher frequencies?
Well, right now we're looking at the first mode and the second mode, basically. The higher frequency stuff we're seeing in the drivetrain, and that we've been able to find in the 11-mouth demonstrator turbine as we're working with ORE Catapult. Right now we don't have one single turbine where you can find the work on the blades, the work on the shaft, the work on the drivetrain, the work on the tower all at the same time. And so Most of the behavior of the system is a first mode behavior. Most of what we're concerned about for foundation life, and our motivation to get into this project is to develop a structural fatigue odometer for the turbine. How many miles does the foundation have left in it? We're very interested in service life extension, and we very much believe that we should be thinking about foundations that can last 100 years as opposed to 25 years, even if you stick a new turbine on top of them at some point. So I think, this question of high frequency data for us has mostly come up, and I'm sorry I don't have slides on it, has come up in terms of into the drivetrain shaft and watching as we're sort of getting individual blade frequencies and different things coming into the shaft along with rotational frequencies. But beyond that, it's a very good question, and sometimes we just completely ignore these high frequencies. So there's the question of when do the high frequencies really matter and how do we capture them and are we modeling them?
Can monitoring techniques be applied after a blade is installed that would define either a repair of the blade or if a full replacement would be required?
The question is for me. Yes, they can be used for mitigation purposes for an existing turbine, and they can flag something relatively small to a large scale. So it doesn't necessarily have to be at the replacement stage. And that's what we are developing is supposed to help wind farm owner operator to run the machine even with small scale cracks and faults and stuff like that, so they can keep making money. But they don't want to run beyond a certain defect or damage scale because they don't want total replacements, which is extremely expensive and dangerous. So yeah.
That's want to contribute?
Sure. I guess if you had a blade profile from the factory and you knew at max chord you had some kind of anomaly that was going to surface, then you probably want to get a monitoring system on that structurally critical section of the blade. So we can work together, Myrent.
And I want to add to that also, the key with a monitoring system is put it on before you have problems. Because if you wait until after you have problems, you don't have a benchmark against which to evaluate your new problematic system. So the idea that this is a practice, that all things are monitored from day one, that's really how you find faults. So we should be careful not to just be chasing problems and installing new systems on them.
And I'll add that that's how you get into the predictive space, is by having a comprehensive understanding of how it degrades over time. And then you use that signature over time. So.
Excellent, excellent. Back to floating wind. Could the timeline for development of your floating models be impacted by the variety of the foundation types, semi-submersibles, spar, TLPs, which all react differently?
Can you repeat the question?
Sure. Could the timeline for development of floating wind models be impacted by the variety of the foundation types, the spars, TLPs, semi-submersibles, which all react differently?
I'm happy to say something about that. I mean, in my former life, I was a structural designer, and so everything we designed was a one-off. And so the idea that there are multiple foundation types to design and that they respond differently under different conditions is a very compelling thing that we should be embracing. But I don't think that as a community we have a clear sense collectively about this foundation responds this way under these loads, under similar loads, this foundation also, responds differently, and sort of where are the gaps and where are the advantages and disadvantages to each system. And I think that's because a lot of the design conversations have been held mostly inside of a competitive frame where knowledge is proprietary. And I think that as we start to think about the reference wind turbines and actually looking more closely at the structural foundations of the reference wind turbines, having the community develop multiple open source reference foundation structures is exactly what we need to be able to say, hey, okay, so the spar, we need to watch this, and we need to be able to talk about it. And I guess the question is are we at a place yet where we can actually talk about it? We can observe they're different, but how do we dig into the detail? And so I think we need to create that space, hopefully inside of maybe the future OC projects, the future IEA Task 37 projects. A lot of these are conversations that are happening. And I think the ability to monitor full-scale turbines and bring this together, public data sets, the United States may be the first to really put out seriously public data sets on these things, and I think this is sort of a question that's been debated for a long time. So maybe some, if we can bring some of those things together, then there'll be a framework within which to enter into those larger questions.
One observation, the best ways to reduce cost of O&M is to reduce hours, labor hours at sea. BOEM did their economics group did a pretty in-depth analysis of what we wanted to know in BESI was how many workers can we expect to be offshore? That's what we regulate. And so that for 30 gigawatts by 2030, the estimate was between 3,000 and 5,000. Again, that's based on operation and maintenance, things we know today. So you can reduce number of labor hours. Another way is to have better diagnostics to detect failures before they happen, which is what we're talking about here, to make sure that crews that are needed for the repairs are properly equipped. Going back to if we keep changing the technology, how do we equip all as much as we need to make sure that they are safe when they go out there. So we've gone through the questions. I did want to ask one that was proposed earlier. Eric, it's going to be back to you, but if anybody else, what are digital twins? Why do we need them? And what is the vision for digital twins?
Right, so there are a lot of different definitions of digital twin. I've seen sometimes people develop a really high fidelity rendering of the inside of a turbine and call it a digital twin. In our opinion, a digital twin begins as a physics-based model, let's say an open fast multi-physics model that has inputs, and this is all theoretical. But then you measure the actual turbine that you're modeling. From those measurements, you use model updating techniques such as Bayesian inference to adjust the multi-physics model. That multi-physics model is now tuned to operate in the way that the real structure is operating. Hopefully, when it's being tuned, we're tuning the right parameters. We're tuning the actual parameters that need to be tuned. This is always a question. And then at that point, one can install virtual instruments, say like on the monopile down below grade, where it'd be very hard to install a sensor. And when you do, they're very hard to protect. We know that from the North Sea. But if we can install virtual sensors, then we can use the digital twin to investigate and sort of interrogate the behavior of the turbine. So again, the idea would be that there would be maybe a small handful of high fidelity digital twins in a wind farm spaced strategically, and then they would be related via machine learning algorithms and transfer learning to the rest of the wind farm, to just a single accelerometer at the top or to the SCADA system. And so the question about networking, when do you need to go high fidelity? What do you get? As soon as you get enough, how do you actually do the rest of what you need to do with a much less expensive and lower fidelity system?
And John, for you, are there enough similarities between operation and maintenance for onshore wind farms that we can apply learnings to offshore wind farms?
Yes, I think definitely. I mean, we're doing that now with, as I mentioned, Siemens 2.3 megawatt wind turbines at Teesside are the same as you see onshore. These are near offshore in this instance, and so in these machine learning models, you're hungry for data, and I think this plays back to some of the earlier questions. It's so critical that the time cost is really tough, and a lot of that is related to getting the data, having the examples, right? Especially if you're looking at new wind farms, you need examples of these events in order to predict them in the future if you want to use these types of models. Which is why I think we can rely on, to the extent it's available, onshore wind operating histories, and we have in the example of delta module failure. So yes, I think it's very important and very, very high value.
Excellent. We've pretty much gone through all the questions from Slido from the audience. It's 10 minutes to lunch. I know that people are probably chomping at the bit. Are there any last points that each of you would like to make based on the questions you've heard, or maybe something that wasn't in your presentation that you wanted to make sure the audience was aware of?
I mean, I can just add one more point. Based upon a question like what's the difference between what we do and some of the other available, I don't want to call them simpler, but more fundamental products out there. I forgot to mention one thing, that on the algorithm side, I think we are far beyond all the capabilities of those products out there yet. I'm sure they will soon catch up and pass us because they're companies, not academia. But we have some, advanced algorithms to process all that high-speed acoustic information we collect, number one. And also in terms of the sampling rates, we collect lots of information that we bleed into the, remotely anywhere we want at this stage. And as the commercialization steps are taken, I think this needs to turn down to a much less amount of data to be proceeded or bled into, to the monitoring side of people. Just wanted to mention those because I forgot.
Yeah, just going back to your point, Sherry, about CRMC having created that provision in the lease. And I think that there have been some very important landmark projects, most notably the RAVE project internationally, where there have been monitoring campaigns. And there has been attempts to have open access, forums in different places, but then it's always hard to get the SCADA data, let's say the structural health monitoring data, the accelerations and the strains, and the structural data for the turbine, all in the same place, all open access at the same time. I don't think that's really been accomplished yet, and I think that the onus really is on the industry writ large, and specifically on the research community and the public sector to come to the table and try to help understand data that needs to be proprietary because it represents an actual competitive advantage. It represents an actual business case. That's one kind of data. But then there's a lot of data that's kept proprietary that doesn't really affect a company's business case. And so far, we've kind of had a black and white mentality towards some of that. And I think that this idea that as a regulator, specifically the DOI managing leases, the question about how are we going to learn, how are we going to innovate, we're going to have to demonstrate all this on turbines. And so the idea of developing a practice that every time we spend $4 billion on a wind farm, there's a little part of that wind farm that goes to advancing the knowledge, and that there's maybe a turbine that's public, there's maybe a data set. The turbines we're talking about now are 6 megawatt turbines. Do people feel safe enough at this point that that's not really the 15 megawatt conversation? And I think to be able to talk about this directly as opposed to making assumptions, this is the single biggest issue involved in the global science of offshore wind moving forward and being able to really encourage innovation from an O&M point of view, from a safety point of view, from a service life extension point of view, to have more available data somehow.
Absolutely. Go ahead.
So I'll chime in on that because I just want to reiterate that if you're an asset owner, that anything streaming on that asset should belong to you. So yeah, any data that's being generated, this is still somewhat of a gap in the industry, and since there was some talk about digital twins and some folks mentioned IEA Task 30, I thought I should mention that we also have IEA Task 43. It's a working group focused on digitalization. A couple areas that we're working in are risk-based maintenance approaches, just holistic, universal, and also gaps in data standardization. So that's looking at during design, during operations, during disposal, what sort of data is generated for a blade, and is it standardized? Where can we start centralizing that, to wind exclusively? So if anyone's interested in learning more, come talk to me, and I can tell you some more about 43. Thanks.
Awesome. Well, thanks so much. I see that lunch is out. Thank you to Corey and Melissa and all the patience for someone like me that is not technically, that is technically challenged. So thank you so much for all of your help. She even had to press the button for me to get the QR code up. So thank you for that. Great panel. Please join me in a round of applause.